It's a great pleasure for me to introduce John Langford. John is one of these researchers who has made lots of important contributions to machine learning and is very well known for them. And it's an honor for us to welcome him today here. He currently is at Microsoft Research, but he has an interesting trajectory of places where he's worked, mostly in industrial life like Microsoft and Yahoo, but at the same time contributing to rather fundamental questions in machine learning in all kinds of areas. And I mentioned a few here. I first learned about his work when he worked on IsoMath, which is a manifold learning method that's been very successful and highly cited. But he's worked on a bunch of other areas of machine learning, including reinforcement learning, bounds, scaling machine learning, which is, I guess, what he's going to tell us about today, hashing representations, reductions, and so I'm really excited to hear what he's going to tell us about in his talk. So, John, here we go.
Thank you. Okay, so I've been working at Yahoo Research for about 6 years, and then Microsoft Research for a year. And one of the things that comes up there quite a bit is you have quite a bit more data than you typically have when you're working with just little data sets people label on their own. So I'm going to tell you about some of the highlights of how you try to learn from lots of data. So when you start looking at this, you see essentially two things. One thing is that you have a lot of data. Okay, so that's sort of obvious, and that means you need your computers to run well and so forth. But the other thing is that the data is odd. So typically, when you have large data sets, like when you're collecting a whole bunch of click data from ads, the nature of this data is not the same as what you would get if you asked somebody to label things. That means you need to take into account exactly how you're getting the data in the process of learning. And that's quite a bit of fun. Okay, so these two things together are really required in order to succeed when you have a lot of data. You need to understand how the different data sources affect your the quality of data that you have, and then of course you need to be able to actually do the learning. The first thing I want to talk about is a large scale data. So when I was graduating from Caltech in '97, I was interviewing for a fellowship for my PhD study. And the interviewer said, "What do you want to do?" And I said, "I'd like to solve AI." And he said, "How?" And I said, "Well, I'm going to do parallel learning algorithms, right?" And he said, "No." It was more bracing than that. This is really, I did not get the fellowship. He said the only thing parallel machines are good for is computational wind tunnels. So that was disappointing. What's even more disappointing is that he was right at the time. Getting parallel learning to work well is not that easy. At the time, there were no parallel learning algorithms, which kind of were provably superior to what you could get on a single machine. So that has changed. So this is a particular data set that I was playing with at Yahoo. There are 2.1 tera features. So a feature here is a non-zero entry in your data matrix. Right? So this is maybe 20 terabytes or so in terms of the actual size of the data set. So this is a sparse data set. You have a bunch of features which involve the interaction of, this is an ad data set, so it's the interaction of the ad with the query. And then you want to learn a good linear predictor, which just predicts the probability of click. Right? So there are, you can measure the size in several different ways. You can say, look, there's 17 billion examples. Or you could say there's 16 million parameters. There's some magic going on here, but I won't really discuss that very much. Essentially, you use hashing to fix the number of parameters. That turns out to work very well. And then we have, of course, these big clusters. So we have clusters with thousands of machines, of which you can easily get 1,000 machines to learn on at one time. Right. So when you're trying to learn a good linear predictor, the question is, how long does it take? Anybody want to guess?
2 hours.
2 hours.
That's how long a grad student is willing to wait for an experiment.
Otherwise, it's sample.
When I started on this project, the data sets people were using were about a factor of 10 smaller, and the amount of time people were willing to wait was about a factor of 10 larger. But when I finished, it was 70 minutes. So the interesting thing about this is that it's actually an answer to this guy. Because you can say, look, there's 2.1 tera features, and it takes 70 minutes, and divide this by that, and it's 500 megafeatures per second. So 500 megafeatures per second, the Ethernet interfaces on the machines are 1 gigabit per second. So the number of bits per feature is certainly larger than 2. And that means that we're succeeding in a real sense. This is faster than the I/O bandwidth of any single machine in the computation. So that means it's faster than all possible single machine learning algorithms. It's no longer the case that it's just computational windows. So it's not, plausibly a feature is 4 bytes or something like that if you compress it well. So it's only clearing that hurdle by a factor of 10 or so. But this is the first time when I've actually seen this, where you can actually take the running time, and divide it by the data set size, and say, look, there's just no single machine algorithm that will ever be invented in the future that can do the same thing. Anyway, that made me feel pretty good because this is the kind of things you remember for a while. Okay, so I want to first tell you about how this works. The essential idea is to use all reduce. So who knows MPI here? Okay, so yeah, so MPI is a message passing interface. It's a library of communication primitives for parallel computation. Now the thing which is tricky about MPI is that so the thing that's tricky here is that this data is not typically stored in an MPI style cluster. It's typically stored on a Hadoop cluster or some other big MapReduce cluster. So starting about a decade ago, people started creating these clusters which have combined data and compute. So you have lots of disks spread all over the cluster, and then you have MapReduce jobs you can execute on them. So who understands MapReduce? Most people. Okay, so for those who don't, when you're trying to do MapReduce, what happens is you divide your computation up into maps, which run on pieces of the data. They each emit a little bit of information, and then you combine those with a reduce. And perhaps you do this multiple times in order to finish your computation. The nice thing about MapReduce is that it can be made robust. And you can just run it on these large clusters and it works. Okay, so the not nice thing about MapReduce is that it doesn't play well with MPI itself. So if you try to, MPI likes to run its cluster, and MapReduce likes to run its cluster, and these two don't play well together. Nevertheless, there's something very cool in MPI, which is it's always primitive. So I'm just going to describe how that works. So this is the initial state. You have a number at every node. And this is the final state. You have the sum of all numbers at every node. Okay. And now the question is, how do you get from the initial state to the final state? So one way to do this is you wire things up into a binary tree. And then you add things up as you go up the tree. So you have 1 plus 2 plus 5 is 8, and 3 plus 4 plus 6 is 13. And then you have 8 plus 7 plus 13 is 28. And then you broadcast this back down the tree. So this is a combination of reduce and broadcast. Okay, so now there's certain properties of this which are extremely important. Naively, you might imagine that going from the initial state to the final state required quite a bit of communication. But in fact, the bandwidth required is just at most a factor of 6 more than the number of bits that you're reducing on. Because for an internal node, you have a number coming in, a number coming in, a number going out, a number coming back, and 2 other numbers going out. So it's a factor of 6. So that's very nice. Another property which is important is that you can pipeline this. So often you want to do all reduce on more than one number, on a vector of numbers. And when you do it on the vector of numbers, let's go back. This operation can be happening, well, this operation can be happening for some of the numbers. So adding up things at the root can be happening while this operation is happening for some of the numbers further down in the vector. So you can pipeline the process. So you can keep, essentially you can be using all of your network links at the same time at near full speed, so that there's essentially no latency concerns. So in a network, typically you have to worry about the bandwidth and the latency. And latency is a non-issue when you have a vector of numbers to do all reduce on. So that's a property. And the third one I think is the most important one. You don't have to rewrite your code. So let me show you this one. All the code that I'm talking about is open source. So the all reduce function is in accumulate, and that is all of the impact on the code. This is code which is optimized. This is VW. This is an open source project of mine, and this is the only place where you actually call all reduce in the main code. Okay, so this is very different. If you have any experience using MapReduce, at least on Hadoop, it's very awkward because you have to refactor your program into MapReduce operations, which involves cutting and pasting a whole bunch of stuff around and essentially changing your algorithm to work with your communication primitive. But here, you just when it's time to sync things up, you just call the all reduce and it runs. So that's fantastic as far as getting things done. Okay, so we coded this up. We tried at first to make things work. The MPI didn't work. Then we made our own. It turned out to be very easy. It only took like a week. And then we optimized it to work in a Hadoop environment. Okay, so in Hadoop, there's certain things that are not nice, and there are other things that are very nice about Hadoop. So one thing that Hadoop does, Hadoop is a MapReduce infrastructure, is it moves your program to your data. So when your program is much smaller than your data, this is a very nice operation. It does this in a way where you don't have to worry about exactly where the data is. So in order to launch VW, to run this kind of computation, you have essentially a map job, which moves VW, the code, to the data. Okay, so then another thing that happens is Hadoop MapReduce is robust to failures. All reduce generally is not robust to failures. Okay, so once you create this communication infrastructure, if a node dies, then the computation dies and you have to start over. That's not so good, right? Now, in a real cluster, the failures typically happen at the beginning. The most common failure mode is a disk failure. So what that means is that if you can delay the initialization of your communication infrastructure until after you've passed the data once, you can restart on a disk failure in the initial pass without failing the entire computation. So that's extremely helpful. That gets rid of at least the first order of magnitude of failures. So that's cool. The last trick is speculative execution. So in MapReduce on Hadoop, if you have a bunch of different map jobs, each of which is running on a piece of data, and sometimes these are very slow because maybe that map job has a bunch of other people, other jobs on the same computer, which are each using the disk, and the disk is getting worn out and thrashing up between the jobs badly. So what Hadoop can do is it can say, I'm going to run the same map job on the same data on a different machine because it stores data in triplicate. So that's nice. We take advantage of the same effect. This is quite important. If we didn't take advantage of this, it would have been 50 megabytes per second rather than 500. Because if you have 1,000 nodes, one of your nodes is going to be slow is quite high. So this deals with sort of the slow node problem, which is pretty significant. Okay, so what this meant in practice for us on real clusters was that we could run VW up to about 10,000 node hours. Now the computation that I told you was about 1,000 node hours, and that was the largest that we found a practical need to actually run. More typical would be 50 or 100 node hours. So are there questions about this? So this is the mechanics of how you actually get the algorithm running efficiently.
So afterwards you are using MPI though on those nodes, the actual communication, or is that kind of mapped onto the Hadoop's reduction step?
So we're using direct network communication.
Okay, MPI similar thing. Yeah, peer-to-peer kind of,
And that's critical. I think, so we spent things at about a factor of 100 over what people were actually using. About a factor of 10 there was just using network communication rather than using disk-based communication.
Right, because there's no centralized place where everything has to be crammed down into.
It's not an issue of centralization because Hadoop itself is decentralized as far as where the data goes. The problem is that if you're writing to disk and you're reading off disk, it's just phenomenally slower than network communication. So that's about an order of magnitude of 2 order of magnitude. The other order of magnitude just has to do with better algorithms. Yeah?
How do you handle the all reduce with the speculative execution? You need to duplicate the communication? Or
So the trick is that if you have delayed initialization and you do it with the right communication protocol, then if a node is slow, it won't begin initialization. And so you have your slow node running for a while, and Hadoop says, okay, I'm going to restart. So you restart on the node, it's almost certainly faster, and then that one will be the one which initializes. And then this one will try to initialize at the end, but the initialization will say, no, die, and it will just die out. Okay, so one of the algorithmic tricks, which was very helpful, was this idea of hybrid online and batch learning. So within machine learning, just kind of just purely for optimization purposes, there's kind of two approaches. One approach is sort of online learning, where where you see an example and do an update. And another approach is batch learning, where you go through all of your examples and then do an update. So in a parallel setting, you can of course do the parallel versions of this. So you can run LBFGS, which is low memory BFGS. BFGS is the first letter of the four names of different authors, all of whom in 1970 proposed the same algorithm. So this is a nice algorithm. Which, the property of this algorithm is that it approximates the inverse Hessian directly. And if you think about the Taylor approximation, if you're trying to get to the minimum of some function, you have the gradient, which is your first order, and then you have your inverse Hessian, which gives you the second order approximation. Right? So in general, you can't use the inverse Hessian because just representing it would kill you. We're working on 16 million parameters, so 16 million squared would not work. LBFGS approximates the inverse Hessian in a low rank way directly. And that means you don't have to worry about inversion, and you don't have to worry about running out of memory, and so it's very helpful. Okay, so LBFGS, like all batch algorithms, is very slow initially. So for the first 10 passes of the data, it does nothing useful. And then you can run this in parallel using all reduce on the gradients, and it gets better and better and better, and eventually it becomes pretty good. Did you have a question?
Yeah, when you're saying online here, are you literally meaning sequential, like each example, or are you doing mini batches?
So what's happening here with online learning is on each individual node, we're running through the data and just doing local updates. And then at the end of the pass, we're averaging the data together. So I mean online learning with parameter averaging. Okay, so online learning in the first pass is going to be pretty useful. And then you average things, it keeps getting better and better and better and better and better and better and better. And it keeps getting better, but you know, it's not converging very quickly to the best. And it's kind of a weakness of online learning. Online learning can take a long time to converge, particularly when you have, so this is the splice type recognition data set. It's one of these data sets where you have a lot of covariant features. If you have covariant features, it becomes relatively important to have a second order method to optimize well. All right, so an obvious trick is you initialize with online learning, and then you switch to LBFGS. Usually this obvious trick is super useful because you're done after about 20 passes. So that's good, it's great. So it works better than, okay, so you can imagine just using LBFGS after 10 passes of LBFGS. And even at pass 30, so it's 20 more passes past 10, it's not nearly as good as. Yeah.
Excuse me, what's the objective?
This is
I know it's
area
evaluation.
under the precision recall curve. So this, every data set has its own particular objective. This is the one people typically use for this data set.
Okay, so is 0.6 or 0.55 good for this data set, or do we have?
Yeah, so we were 0.01 better than any published result on this data set. Not really significant. Essentially, we're doing the same as it's been done previously, but much faster. So I guess one question is, why does this work so well? We're doing much better than, so 1 pass of online and 19 passes of LBFGS, he's doing much better than 30 passes of LBFGS. And so my best explanation for that is that when you're doing online learning, you're doing very rapid updates. And that means that in terms of the dual, you can kind of make rapid progress. So when I say the dual, what I mean is you can think of the weight vector as a combination of the weight vectors of all the individual examples. So you can kind of, this is intuition, but you can get the dimensionality of the weight vector in terms of the dual can be much higher when you're doing online learning than when you're doing batch learning. When you're doing second order batch learning, however, you can make big steps, and that can be very powerful. So the combination of the two seems to work together very well. Anyway, if you're doing CS optimization, it's not always the case that online takes a long time to converge. There's many data sets where online seems to just get you to the solution that you want. But the combination of online followed by LBFGS, I've not seen fail. Yeah?
Well, how about the interpretation of this? Initially, your parameters are so bad, they're random,
Yeah.
that any progress you make is going to help you. And if you can do that progress quickly, why not?
Sure, I mean, that's obviously, that's a reason to do online, but it's not a reason for LBFGS at 30 passes. See, LBFGS at 10
At that point,
passes is the
at that
same
point,
as
you've done one
online.
step from a bad initialization, right? So if you just do your first, 20 iterations online and then switch over to BFGS to sort of finish it off,
Yeah,
it seems like that simple recipe has an intuitive interpretation, right? Like get somewhere reasonable quickly,
Yeah.
and then
Yeah.
second order it.
it's definitely what we were thinking about.
Yeah.
I guess what I'm saying is that if you look at here, and you go over that far, so like that, you see that purple is doing very well. So switching over at 1 is quite good. If you start here and you go this far, then LBFGS still is not doing as good. Right? And that's kind of strange. Because the initialization points are essentially the same to performance.
Is this training performance or out of sample performance?
It's out of sample.
So could it be that stochastic gradient online is finding sort of well, I guess this is a convex problem, right? Is it?
No.
It's not?
The metric here is not convex anyways. It's just area under the
But what
precision
it's
interval.
optimizing is convex.
Yes, that's true.
So in the non-convex setting, online is believed to have the advantage that it can find, escape poor local minima, but it could also escape poor regions even in the convex setting faster.
Yeah.
That might explain why LBFGS is kind of stuck for a long time before it escapes, whereas online can escape very quickly.
So I think just the fact that LBFGS takes 11 passes to do something useful just has to do with batch algorithms. There's a minimum number of steps to do anything useful here,
Right.
and batch algorithms just take a long time to take a minimum number of steps. Okay, so we also compared some other algorithms, and of course, we're doing better. So this is Marty Zinkovich's approach. So here, what happens is you do online learning on every node. Okay, so what you do is you create an overcomplete partition, so that every example is on 1/4 of the nodes. So that involves a lot of shuffling of data, and then you run online learning on each of the individual nodes, and then you average things at the end. So that's the blue. And then this is mini batch here. So this is related to your question. So the idea here is that you run through a bunch of examples in each individual node, and then you average results. You average the gradient and then you do an update. And you just keep on doing that over and over and over again. So this graph understates the value of this algorithm, because this is just talking about the prediction performance. In terms of computation performance, this point is much faster than this point, which is much, much faster than this point. This was 40,000 node hours. 40,000 was difficult to do. It's the kind of experiment that's not so easy to repeat. Because if things fail, you have to restart. Okay, so why does this work better? Well, we're working better than this approach because we're communicating during computation more. So we have more coherent optimization going on. Also, I think the combination of the online plus the batch gives us a substantial lift. If you think back to here, where I was talking about, so you can see that just online alone is really cutting the mustard. And then why is it better than here? So there's a lot of communication going on here. So there's a lot of synchronization, but mini batch alone, especially with the mini batch sizes that were required in order to amortize the communication, you end up having a very large mini batch size, which means that you fall into the same kind of problem as LBFGS taking a long time to initialize. But it's worse than that because the mini batch approach wasn't second order, it was only first order. Okay, so that's handling the computation. And now I want to talk about how the data itself is kind of off. Are there questions about the computation? The optimization?
So how do you look at non-convex optimization?
Yes. So the same kind of, so when you're doing non-convex things, you can't do parameter averaging because it just takes you into crazy space.
Did you try?
I went and visited Dion LeCun's lab, and I talked to Clement, and he implemented, he took the all-reduced library that we created, and he put it in the torch. We tried it on some neural networks, and indeed it went into crazy space, as you expect. LBFGS is still a valid algorithm, but LBFGS without initialization feels pretty, limited. So we have a paper that we submitted to NIPS just now, talking about using active learning techniques in order to speed up parallel learning for non-convex implementations. So another project which I'm not going to really talk about in great detail, is we've been figuring out how to do active learning. So, and one of the difficulties with active learning is that most of the criteria which exist don't work if you have any noise.
So can't you just do mini batch SGD, asynchronous SGD, or something like that, like standard for the first debug and then LBFGS?
Yeah, so mini batch, so asynchronous is a very dangerous word in my experience. We've experimented with various asynchronous parallel algorithms and always been dissatisfied. So this is not my first attempt at parallel learning. This is probably my third attempt. And asynchronous has a severe problem in practice that you just can't debug it. I mean, you run it 2 different runs, you get different results, and if you change something, you get a different result. Was it because you were unlucky or lucky, or it's just not clear? So I try to stay away from asynchronous algorithms, to the extent possible. Now, there's limits to that. If you have very widely distributed computers, then you have to go asynchronous. But even in that case, I think what you want to do is you want to have a synchronous algorithm that you can debug, and then you want to deploy it in asynchronous fashion. I have debates about this with people at times. Okay, so
Just a quick question, John. How many nodes do these kinds of results start to pay off? Like, do we need 1,000 nodes? Can we do this with a few dozen nodes?
most of it just kind of depends on your data set. What I saw at Yahoo was there were some data sets which could actually justify using 1,000 nodes, like some of the big click prediction data sets. More typically, you'd be like 50 nodes or 100 nodes. If you took a look at your communication time versus your computation time, so your computation time is dropping as you have more nodes. Your communication time is increasing. hopefully it doesn't increase too quickly. And then, there's some sort of minimum, which is the point that you use. So that point was often 50 nodes or so. Right? Even if you're running on 3 computers, you're still going to see some improvement. Obviously, it will be limited by a factor of 3, but
So the
factor of 3
communication
can
overhead
feel pretty good
doesn't.
if you have a long application. Yeah.
Maybe me, question. If in practice you end up having to do these cross-validation things over lids, does that ever just make it easier to just coarse grain parallelize it and run your cross-validations in parallel? Or is it a way to like take advantage of some kind of extra?
Yeah, so when people are doing machine learning practice, they're often doing parameter search or hyperparameter search, basically, one way or another. And a crude and simple way to use these big clusters is you have a bunch of individual nodes, and each of them sucks in all the data with the thing with its own parameter setting, and you just compare the results from different parameter settings. So that is, I think if your data set is not too large, that's a very reasonable thing to do. And that works fine as far as your overall workflow. These data sets were large enough that you didn't really want to do that. Right? So if you suck 20 terabytes into a single machine, it's not going to be happy.
How about copying the data in the first place to all these machines? Isn't that the same load?
So I think the idea is that you copy the data once into the system, and you don't ever copy it again. Right? So you pay the cost of moving the data once, and not every single time you do an experiment. Okay, so this is kind of, okay, so when you're trying to look at how people get data, it's often rather different from paying people to label data. So maybe you're displaying news stories, and you want to decide which news stories are going to be of interest to people, right? So maybe a user comes to the company, they have some history of previous visits, maybe an IP address, maybe they have some data related to their account. You choose some information to present, and then the user reacts to this. So the thing which is important here is that if you display news stories about the Packers Saints, you're not going to know anything about whether or not people are interested in Benghazi or in the Harper government. you don't have any information to make that judgment. Okay, so this is rather different from supervised learning. In supervised learning, you have somebody who labels things and says, this is what the right answer is, or maybe it's even cost sensitive, and they're saying, oh, this is a good answer, and that's a bad answer, and this is an okay answer, and so forth. Right? So here you don't really have fully supervised information. All that you have is partial feedback. All that you know is, did they click on the particular story that you happen to choose? Right, so it gives you some interest of it gives you a notion of how interested they are in what you chose, but not how interested they are in what you did not choose to display. So that's a very different kind of setting. Here's another example of this. This is clinical decision making. So I guess presenting news stories or ads or whatever is kind of frivolous in some sense, but this really matters. So a patient comes to a doctor, they have symptoms and some medical history test results. The doctor chooses a treatment, the patient responds to it. This is the same kind of structure where you only get information about the actions you actually chose. So typically you don't know what would have happened if they had given you a different treatment. And now you want a policy for choosing the best treatment. So this is, I stopped taking the medicine because I prefer the original disease to the side effects.
That one has potential ethical side to it as well, in that what would allow you to learn the fastest may not
pretty good for people who are taking the medicine too, which is interesting twist.
Yeah, so there is just kind of an ethical problem there, but the standard for medical trials is in fact randomized trials. Now the particular way that they do the randomized trials turns out to not be optimal as far as, you know, minimizing the number of deaths. So I think there's a lot of political issues and basically non-technical issues associated with exactly how trials are run. But
Or do they allow more deaths in a trial to reduce the number of deaths later on after it, you know, comes to market, things like that?
okay, so what the mathematics suggests you should do is you should not regard, you shouldn't think of things as just having a trial. You should have some initial exploration, and then if you have encouraging results, you keep on exploring over more and more and more until you know, the new treatment just kind of takes over everything. So you don't have discrete trials. You have constant monitoring, and the amount of exploration that you're doing should be dependent upon the quality of the outcomes that you're observing. If you do that well, you should be able to do it substantially better than the current clinical trial system. Okay, so this is the contextual bandit setting. This is to formalize these kinds of operations. So you have an online setting where you're running through individual examples. You see some context, so you see some features. You choose an action, and then you get a reward for that individual action. And now you want to learn a good policy choosing actions given context. So a policy is something which maps features to actions. You have a set of policies. So in learning theory, the way that you describe I learn is to say I have a set of policies and I compete with the set. So that will mean for us is regret. So we're taking a look at the best policy in the set that has some particular average reward, and then you have the reward that you actually observe. You want your regret to be small. So you want to compete with a large set of policies while having a small regret. So in learning theory, there's actually two different ways we talk about learning, and they end up being very similar to each other in terms of the kinds of bounds you can prove. One of them is a regret type bound. The other one, you have some sort of assumed distribution over events, and you talk about your average reward compared to the best policy's average reward. Okay, so what are examples of the policy? So it could be just what is the best single action? What is the best single action? So this is what clinical trials typically get at. Should you treat with drug A or drug B, or drug A or no drug, or drug A or drug B? Just what is the best single action? You could have your set of policies be the set of all linear predictors. Would be a common choice. It could be all decision trees. You could have it be some discrete set based upon domain-specific concepts. So if you only talk to a doctor, you could say, when do you think we should treat? And then you can talk to another doctor and say, when do you think we should treat? When do you think we should treat? You could write down each of these policies as a rule, and then you try to use contextual bandit learning in order to optimize for the best. Okay, so in machine learning, so there's kind of a tension between machine learning and statistics. And one of the core reasons why there's a tension is because statisticians often like to do math and say, this is the right approach to doing things. And machine learning people, I think in the beginning in particular, were very much into just doing things. So so statisticians would say, oh no, you need to write down your assumptions and understand what the right thing to do is given the assumptions. And the machine learning person would be just like, no, I just ran the algorithm and it worked. See? You can't do that here. You actually have to understand the statistics of what's going on. you can't just follow your nose in the contextual bandit setting. You have to explore to succeed. You have to understand how to incorporate the exploration information properly in order to succeed. That's critical. So thinking back, you just can't determine whether or not you should be presenting a news article about Quebec versus a news article about some sports team if you only display sports teams. The information is not there. Okay. One other approach people use to describe these is in terms of a bandit problem. So a bandit problem is the same as a contextual bandit, except there's no X. That means the only set of policies that you can really compete with is the context-free policies. Okay, so you can, of course, decide to ignore all of your assigned information. You can ignore the observations about, you can ignore this, the symptoms, and just come up with treatment. Actually, by the way, that reminds me of when I was at Caltech, the joke was that if you went to the healthcare center, they had two prescriptions. One of them was drink water, and the other one was let's do a pregnancy test. So you can, of course, choose to ignore all your symptoms when you come to treatment, and that's very limited, right? In practice, when you're at a company and you have somebody who's actually applying machine learning even badly, often they will provide superior performance to somebody who ignores the features and does conduct just plain bandit learning. Okay, so generalization across X is required to succeed for these problems. Okay, so now the first things you want to do in these settings is you want to know when you've succeeded. It's non-trivial to know that you've succeeded because you have actions. I mean, if you come up with a new policy, you have some data from the past, you come up with a new policy chooses different actions. So if your new policy chooses actions which are entirely different from your recorded data, you have no information. And so you can't even evaluate your new policy well. So the question is, how do we create a system for evaluating policies?
Introduce noise.
Random exploration is indeed the answer. So the naive approach, of course, is you just so if you randomly explore with actions, you're going to have features, action, and reward, and implicitly we're uniform random over the different actions. Okay, so now, it's kind of a tricky thing here. So when you're exploring randomly, if you have a probability of the action, then you actually do want to record that and use it. But if you don't have a probability, there's often a trick, which is that you can estimate the probabilities directly. This is essentially multi-class probability prediction. Right? You can estimate the probability of the action directly. You can also build an estimator of the reward directly. So one of the simpler approaches people try to use is just build an estimator given the features in the action, what is the reward. And that kind of works, but you better have exploration data or else it's not going to work. And it's really, you can do something even better. So you can combine the p hat and the r hat to create an estimator of the value of a policy. So a policy number is something which maps features to actions. You take the average over your data of reward minus your reward estimate. This is indicator function of the policy choosing the action, divided by the estimated probability of the action given features, plus the estimated reward. So this is the double robust estimate for the value of the
So
policy.
why is not p hat just the indicative function of phi of x equals a?
So the idea is that we're doing random exploration. So this is
Like your
this
pi-
is this is the probability for the exploration policy, not the policy we're trying to evaluate. So we're randomly exploring and choosing the actions.
pi is not the same as the exploration policy.
Right, and that's key. So we want to be able to record data just like in supervised learning, and then evaluate policies offline later.
But these are deterministic constants.
This pi could be deterministic. You can also, if it happens to be randomized, and you make this be the probability that pi of x equals a. Oh, and you need to adjust things here too. You take the expectation, respect to the policy of the reward. So this is the double robust estimate. Okay, so if r hat is the expectation, then they claim this gives you the right answer, because the expectation of r minus r hat will be 0. Right? So this term will go away if r hat is the correct answer. So if you have a very good reward estimate, you win. If you have a terrible reward estimate, and you have a good probability estimate, that turns out you also win. So this is a little bit tricky, but suppose that r hat is equal to 0. Right? So then this term goes away, this term goes away. This is the reward times indicated function of probability that features the action divided by the probability, and that also is an unbiased estimate. In any combination, so you have kind of two ways to estimate that are combined here. So if you err, so if your reward estimate differs from your expectation, and your probability estimate differs from the truth, you can prove a theorem which says that the error in your estimate is bounded by big delta times little delta. So when I was growing up, my mother would say, 2 wrongs don't make a right.